Hello everyone, I'm Yu-Cheng, a master's student supervised by Professor Pei Yan at the University of Aizu. Today I'm excited to share my research on content generation of computer game using interactive evolutionary computation. This work aims to tackle one of the biggest challenges in game design, creating diverse and high-quality levels that align with user preferences. Designing game levels is a complex and time-consuming task. It requires creativity, effort, and constant iteration to meet design goals. While AI can assist in generating levels, the challenge lies in balancing quality, diversity, and user preferences. Even if an AI-generated level is high quality, it may not match the designer's personal style. To address these issues, we developed an innovative approach that integrates human-computer interaction with AI-based content generation for Super Mario Bros., one of the most iconic video games. By applying this approach, we aim to generate higher quality and more diverse Mario levels that better align with player expectations. Moreover, our method addresses the limitations of existing approaches, particularly their tendency to produce single-style levels and suffer from feature entanglement. Let's explore how our framework works. Procedural content generation, or PCG, is a powerful game design technique that reduces development costs while enhancing replayability, diversity, and scalability. Generative adversarial networks, or GANs, consist of two neural networks, a generator and a discriminator, working together to produce high-quality content. Interactive Evolutionary Computation, or IEC, enables human users to fine-tune deep learning models by adjusting latent variables, ensuring the generated content aligns more closely with personal preferences. By integrating these three techniques, we aim to generate customized levels for Super Mario Bros. Now, let me introduce our programming framework. We use Python with the PyTorch framework to train our model. Java is used to provide interactive interfaces, render level content, and implement game logic. Our framework consists of two main components. Part A, a pre-trained StyleGAN-based generation model, and Part B, an interactive evolutionary process for user-guided manipulation. The process begins with Gaussian noise input, which generates an initial levels. Users then select their preferred levels through an interactive interface. If only one level is selected, single-point crossover is applied. If multiple levels are selected, uniform crossover is performed. Finally, through the mutation, and the next generation will be generated. And this iterative process continues until the user finds the solution. StyleGAN improves upon traditional GAN architectures by reducing feature entanglement and enhancing both the quality and diversity of generated levels. For level rendering, we utilize the VGLC method, which converts annotated text files into visual game icons. It looks something like this. Now, let me show you a quick demo. Here, you can see our interactive interface. At the top, we have the current generation and a few control buttons. Below, 5 generated levels are displayed. If you don't like the current selection, you can press the reset button. If you find a promising level, click on it to evolve further. The default mutation rate is set to 0.2, but this can be adjusted before proceeding with evolution. Through IEC, we can observe that these offspring levels are derived from its parent level. Let's try playing one of the generated levels. The game mechanics function just like Super Mario Bros. If the player reaches the end, the level is successfully completed. If the player gets hurt too many times or falls into pits, it means the challenge has failed. If the level is satisfactory, it can be saved as an annotated text file for future use. However, to achieve the best solutions, the IEC process requires sufficient time and generations to refine the levels effectively. Now, let's discuss our experimental setup. We recruited 13 participants and asked them to generate levels they were satisfied with within 5 minutes. The goal was to compare the performance of our proposed framework with existing Wasserstein-GAN-based approaches. As shown in the figures below, the levels generated by the two models exhibit distinct styles. In this page, we used several standard image evaluation metrics for generative AI to objectively assess our framework. The Fréchet Inception Distance, or FID, evaluates image quality, with lower scores indicating better performance. However, since FID alone doesn't fully capture fidelity and diversity, we also used precision, recall, density, and coverage for a more comprehensive analysis. Our results demonstrated that our proposed framework outperforms previous models in generating diverse and high-quality levels. In this page, we designed a questionnaire based on a 5-point Likert scale to understand the subjective opinions of participants. This survey, including 3 questions, evaluated the perceived quality, diversity, and uniqueness of levels generated using the StyleGAN plus IEC approach. From this chart, we can see that participants generally agreed that our framework significantly improves the uniqueness of generated levels, followed by diversity, and then quality. Although our framework performs better than previous methods, we wanted to take a different approach to evaluating user satisfaction. To measure this, we used the Net Promoter Score, NPS. NPS is an industry-standard indicator for gauging user satisfaction, loyalty, and overall experience. Participants were asked, "How likely are you to recommend this framework for Mario level generation to others?" Responses were categorized into 3 groups. Promoters, who scored 9 to 10, indicating strong loyalty. Passives, who scored 7 to 8, meaning they were satisfied but not strongly loyal. Detractors, who scored 0 to 6, representing dissatisfied customers who might leave negative feedback. NPS ranges from -100 to 100, and the definition of what is a good NPS score depends on the industry. Generally, higher scores indicating more positive user reception. In our case, the responses from 13 participants resulted in an average score of 5.54. This appears slightly above the midpoint. But using the formula in the upper right corner, we can see that the NPS was calculated to be -38.47. A negative score indicates that the number of dissatisfied users exceeded the number of satisfied ones, highlighting areas for improvement. In this study, we proposed a game content generation framework for creating high-quality and diverse Super Mario Bros. Levels. We also conducted a comprehensive performance analysis from multiple perspectives. While the framework demonstrated promising results in traditional evaluation metrics and user assessments, it still falls short of fully meeting user expectations, highlighting areas for further improvement in recent Mario level generation research. To further enhance our Mario level generator, we propose several improvements. First, we can introduce more constraints to ensure that generated levels are more logical and playable. Second, we can filter out levels that are too simple or lack sufficient challenge. Finally, incorporating additional user satisfaction metrics, such as the Customer Satisfaction Score, CSAT, and Customer Effort Score, CES, can provide deeper insights into user experience. I am confident that these improvements will significantly enhance our framework's effectiveness and usability. Thank you for your attention.